So welcome again, and good morning, good afternoon, and good evening to all of you. Thanks for joining today's webinar about floating solar PV on water reservoirs. As you might know, today's webinar is part of our Future Grid Week, a week with 3 webinars related to all of our future grid labs. Last Monday, we had a webinar on the rising value streams of energy storage. And last Wednesday, we had a webinar on integrating large-scale renewables using microgrids. Both of these webinars can still be found on our website, thefuturegrid.com, and the recordings can be accessed through that website, and the slides are available online. Today's webinar will feature Tobias Haarburger from Continental. He will talk us through floating solar PV on water reservoirs. But before we start with this webinar, I want to notify you on Future Grid Week. It ends actually today. I see that the timer is not good. It's till the end of today. You can get a 20% discount on your tickets for the Future Grid Labs using the promo code FGWeek-20. Use it on the registration page and your ticket will be discounted. Besides that, I want to notify you on our Future Grid, thefuturegrid.com. You all in the webinars here know about our free webinars, but we also have free reports and articles coming by on that website. You can sign up for updates and you get this all in your mailbox for free. So back to today's webinar on floating solar PV on water reservoirs. It's about the PV cell integration on a membrane material and the advantages of floating cover on water reservoirs for farmland irrigation. Before we start, I want to give you some practical details. Please use the chat box if you have any technical issues. We'll help you over that. And you can use the question box to ask questions to the presenter. You can send your questions throughout the presentation, and we'll have a Q&A session at the end of the presentation. So you can already send it before we enter the Q&A session. Besides that, the slides will be available after the webinar, so that's often the most asked question. They will be. So now we're going to start with the presentation by Tobias Haarburger. He's the program manager of solar power applications at Continental, and he's in the lead for the PV application they have on water reservoirs. So Tobias, I'm going to hand you the controls and start your presentation, and then the floor is yours.
Okay, Thomas, thank you very much. And thanks a lot for giving us the opportunity to present this innovation. The title of this webinar is Solar Floating Cover on Water Reservoirs. We are focusing on farmland irrigation. With this innovation, I would like to say a word. How can I start the next slide? Thomas, okay. Just a word about Continental. Continental is mostly known as automotive component manufacturer. Became a very large industry group in the past 50 years, employing more than 200,000 people. Continental is producing, and that's probably the most known product, tires for cars and trucks. But it's organized in 5 divisions. So Contitech, this is where I belong to, is an industry division, also employing more than 40,000 people, so large structures here. And then the typical automotive divisions on the other side. I have joined Continental about 8 years ago. My personal background is water treatment. I'm a graduated engineer. And so my job there is to carry out innovations in the water and environmental market. Okay.
Tobias, if you click the screen once, and then you can use the arrow keys on your keyboard to move the slides.
All right. Okay. So this innovation we have done is focusing on farmland irrigation. It is a niche within floating solar. And the purpose of this innovation is not only to produce electric power, but to improve the hydrobiological quality of the stored water. And this is okay, what I will explain now. So you will hear some words about water storage, water quality, etc. And this is an overview presentation. Now I will speak about these things: farmland irrigation, then photovoltaic, of course, the hydrobiological advantages, installation and logistics, and also the economics. Okay, so in general, the reservoirs we are focusing on are not that very large ponds with, let's say, more than 100,000 square meter. Farmland irrigation ponds are storing, or reservoirs are storing, water of a good quality. On one hand side can be rainwater, but on the other hand side it's treated wastewater usually, which is then used within the farmland irrigation scheme. So that means usually reservoirs are existing there. So there are, in some countries which suffer from water scarcity, are thousands of reservoirs already. And it's rather unusual to build new reservoirs tailor-made for this application. So we have to be able to adapt the shape and the dimension of existing reservoirs. And that's why we learned in the very beginning we have to have a system which is free floating on one hand side, or we cover the complete area. So of course there are technical impacts on the in all directions, and I will explain that. What are the effects on that? Oh, sorry. Okay, let's go back. We have installed back in 2012 a test reservoir, or our open space lab, so to say, in Israel. It's not that one, that's another one. But we had to learn, and this is the key of the innovation, was how to connect solar panels on a cover, on a floating cover, which was once developed to resist and to refuse any attachment, whatever it is, because it has to stay at least 20 years freely in the environment. And this is similar on the panel backside. The backside material, the backsheet material, is usually something like Tetlar. It's a trading name. So this was not that easy to find a good solution for this. So what you see here on that slide, and this shows the general concept, it's a project in the Mediterranean. It's a rather small reservoir. The local authority asked for a proof of concept, so we have done that. And what you see in the background is a typical wastewater treatment plant. It's tertiary treated water, so three times treated. It's a rather good quality, and it's going to be used for field irrigation for farmers in the area. This floating cover is has an area of 6,500 square meter. The reservoir is 4 meters deep, and it stores about 24,000 cubic meter. And the reservoir itself is 20 years old, and our job was to carry out this project turnkey in order to have a platform for photovoltaic. And each reservoir usually has at least a pump station to consume the electric power, but usually they also nearby electrical grids, local grid. So the self-consumption schemes can be connected or shall be connected as well. Okay, I'm too quick, sorry. So what you see here is how does it look like exactly. So you see here the panels on this first phase of this project. There are only 80 panels. We were, naturally, it was an innovation, so we were a bit conservative and didn't want to install 2,000 panels or so from the very beginning. It turned out our method is working very well, so we will do that sooner or later. So the cover which you see here is following the water level, going up and down. This is a part of the design, so there's some engineering has to be done before. What you see here is a trench consuming the cover material and releasing cover material when it's going up and down, because the cover has to be under tension all the time. Also in the Mediterranean, it's raining between December and March or so, can be lots of rain, heavy rain. So rain and photovoltaic doesn't like each other. So there are pumps installed. Here we have installed 4 pumps, submersible pumps, and they have to remove the rainwater within, we say, 48 hours, and this will work. What you see else are stairs to walk on it from outside. These are manholes and aeration devices so that divers can go in. There's not much to see underneath of it, but because we cover the reservoir for, let's say, 20 years or so, of course, it must be possible for a person or for divers to go in. Okay, so again, the general concept, why are people doing that? So first of all, the pump station, I have not shown a photo from this, but it should be self-sustainable pump operation. This reservoir is nearby this wastewater treatment plant, so there's lots of energy anyway for treating the water, but quite often they are a bit more remote. So it's a good advantage to have their own 100% electric power production for the pump station, or even for water treatment, and this is also there available. So secondly, the participation on the renewable feed-in scheme, I don't need to explain that, that's known. Then replacement of alternators generators, that means calculating photovoltaic against diesel. There it's very quickly beneficial to have photovoltaic. In general, the water and power supply in semi-arid regions is an advantage, not that much on the northern side of the Mediterranean, but on the southern side, the side where these very large countries like Algeria or Morocco or so. So even a complete chain of reservoirs can be erected. So saving land or land costs, I mean, we all know that people who are involved in floating solar know that in Asia it's very much about available land. So land costs, this is a shortage. But it's not only the land as such, it's also the infrastructure. That means having a reservoir and the cover on it, so the infrastructure is ready. So no additional fence and nothing has to be built in addition. Then the photovoltaic itself is state of the art. We took it out of the shelf. We didn't develop much on it yet. We will probably in the future, but not now. And then the question, I will describe it more in the next slides. Which kind of panels do we use? And that's something I will explain now within the next slide. So glass encapsulated PV panels or fully flexible or semi-rigid panels can all be used. So this is an example also in the Mediterranean, typical reservoir water treatment in the middle. And now the question is, how does it look like when there are photovoltaic panels? This is a rather simple sketch, a pre-sketch for a simple pre-design we have done so far. But you can see we speak about thousands of panels and small power plants in megawatt size. And so therefore the complete logistic chain, which I will explain later, is of great importance. So there's a lot of hand work to be done. So now about photovoltaic. As usual, I have to do an engineering, the loading profile analysis, energy yield simulations, all the typical pre-planning things have to be done. This is both routine, can be done by every expert. Then the energy balance, feeding concept, the same thing. except when a reservoir is really remotely somewhere far away in the landscape, then it's a bit different. The nominal power per area, we say for the time being that up to 60% of the floating cover area can be utilized for individual single PV panels. So there cannot be one panel on the other, like on a large free area system. But that's quite a lot, and so usually the reservoirs we are looking to have an area between 10,000 square meter and 50-60,000 square meters. This is the typical size. Then of course there are larger ones with 100,000 and so on. So, and again, this results as a rule of thumb in about 600 kilowatt peak per 10,000 square meter. So the floating cover is fully walkable. The material we are using is made of PVC. There's a scrim within the material, within the floating cover. It's a 3-layer system. And so all the service, all the sometimes exchange of panels or whatever can easily be done by a service team. Then again, the design panel inclination and orientation is typically as for every other plant. There's usually not much shadow or even no shadow in the area of a reservoir. And so according panel design, horizontal roofing panels without inclination can be installed. So as I've seen before on the other photo before. And regular rigid panels according local conditions. That means wherever the reservoir is or the direction, the orientation has to be chosen accordingly. Okay, so this is a slide just showing that there's nothing special on the photovoltaic side to be done. So we work with PV-Sol, the other big software is PV-Syst. Perhaps there are more, but we are working with these two, mainly PV-Sol. And then we do a typical design and wiring diagram, etc. So experienced or every experienced photovoltaic design company is able to do the design for it and the engineering. So now about the equipment. So we have in the very beginning, when we started in Israel with these test reservoir, the market was different. That's some years ago. It was back in 2012 and 2013. We installed a couple of horizontally installed CIGS panels, or even amorph silicon was available there. It worked very well, but so some vanished from the market, and some others turned out to be simply not that economic. So now, for the time being, I think there's no other choice than to use regular panels, aluminum framed, glass encapsulated. And the method at the end of the day is very similar as for roofing. You see here on these black sub-construction is from the company Renault-Sol. It was developed for flat roofs. We believe it's a very good system. There are other manufacturers. That's just an example I'm showing here. So this can be installed on the cover in order to have the inclination which is needed. And then it's going to be fixed with a method we have developed with the same material at the end of the day we are using for the floating cover. So to install the panel is not this big challenge. It's a bit different with the cabling because we have to avoid that cabling is disappearing in rainwater. But also this can be solved. Then the inverter will be outside the reservoir, and our monitoring and everything is outside, so that's no question. This little plant, this little reservoir you have seen before, there the cabling on the photo was not installed in that time. It was taken very, very early. But again, the rule we have set up for ourselves is that no water shall stay on the reservoir longer than 48 hours, but vice versa. That means for some hours or 2 days, the cable can be underwater. So these have not created problems yet, but it increased the overall costs, I guess. Okay. So the installation, one question is the panel allocation and the distance and the accessibility. So we have started rather conservative. We believe, as I mentioned already, in this 60% overall cover. The floating cover is not rigid like a concrete roof, of course, but on the other hand side, it's also not that difficult to work on it. So if 2 technicians are carrying a 20 kilogram photovoltaic panel, it's no problem to work on it and to service it and perhaps to exchange a panel over time or so. So the distance we said should be between 20 centimeters and 50 centimeters from one panel between the other. The subconstruction fixation I mentioned already is by hot air welding. It's quite similar like you install roofing material. That's not rocket science, but like always, you need to have people who really know how to do. We are not using metallic fixtures at all. We cannot perforate the cover naturally. So we install it in a method which is kind of embedding with cover material. The rainwater management I have explained. So we have decided in these little reservoirs to use more pumps than necessary to have a redundancy. This is like every pump installation is done with redundancy. So it's also a bit of cost question. Not only the pump itself, these pumps doesn't cost so much, probably less than 500 euro per piece. But again, the cabling, etc. This then costs some money, of course. So cleaning is according to the routine method. Water is available. This makes it quite easy. And repair the panels also like usual. Let's say once in 3 months, or depending on the environment, and in desert areas it has to be more often. Okay, so that's nothing new for the audience, I guess. The loading profile. Usually water pumps have very large motors. So for the time being, we had no project where the photovoltaic produce more power which is consumed by the pumps. But as we know, if there's no battery storage, there must be a feed-in scheme, a net metering scheme, and if this is available locally, then it's clear how the economic scheme will be organized. Okay, so this is an image showing a bit better how we installed it. These panels are crystalline silicon. They are semi-flexible, very stable. They have no glass encapsulation. We have installed a kind of a foam underneath to have some distance between the cover and the panel top side, front side. And it worked very well, and the installation was much more quick than we thought in the beginning. Okay, now I leave the photovoltaic part and go to the hydrobiological advantage. So this is about water technology. So why covering a reservoir completely? So the floating solar, as we know from the market leader, CATL, so they shadow the water, but it's not completely covered. So what we do, we change the water quality or the water quality from aerobe to anaerobe. So that means no oxygen can go in anymore and no light is going in anymore. So why it's done that? This is not our invention, of course. I mean, this is a method which was developed in the US, I think, in the 1950s or so. And there are worldwide, must be hundreds or even thousands of reservoirs covered with a floating cover of different materials. It's a method to improve the hydrobiological quality. So it prevents completely evaporation. And the side effect is that salinity is not increased anymore by evaporation. So it's not only the water itself which evaporates, but also the salinity, which is quite disturbing for farming, is kept on the natural level which the feed water has. So another thing is the massive primary production of algae. This can happen because we speak here about tertiary treated wastewater. This is where we are looking in. And if it's rather fresh rainwater, the algae growth is much less. But we have now seen many cases where reservoirs suffer very much from algae growth. And in addition, there's odor and pollution and so on. So farmers complain about it. And the irrigation equipment is suffering from that. So these are the reasons why reservoirs can be covered. So I don't go too much into these details. There's some research going on, I learned recently, which is very important, because if this trend continues to install floating photovoltaics, so both have to be examined, the shadowing of the water area, but also what we are doing, the complete coverage. So the second slide here on the hydrobiological part answers a bit what can be done in order to improve the hydrobiological quality. Also there, engineering or lots of monitoring has to be done. So usually when water looks like here on this image, a hydrobiological or a water biological expert has to be involved. So this shows also that we speak about two completely different techniques, photovoltaic and water management, water treatment. The water treatment cost, by the way, can be rather high. So for the economic feasibility, it's very important that somebody looks into that part, which understands the savings of chemicals, of energy for water treatment, etc. That's very, very important for the overall economic study. So now this slide should easily explain where the water can come from. So in countries with water scarcity and desalination is used, and desalination is only installed where is water scarcity, because it's quite expensive, very much energy consuming. So there are two storage parts usually. The so-called permeate, the potable water is stored and then used for urban consumption, for drinking water, potable water. So, and then the wastewater is going to sewage treatment. And then it's stored again. So there are two parts in the complete chain, consumption chain, where a solar floating cover can be installed, and then this treated wastewater can be used for dryland irrigation. So that means the communication with local authorities in order to develop projects, this is quite important. And we learned that let's say the sales team or the team which is developing the project needs to have a good knowledge of both, of water technology and photovoltaics, which is not all the time given. That's a little obstacle, but on the other hand side, there's no other way to do it. So now farmland irrigation, I think this is more or less known, the main methods. These are different sprinkler systems. It's a bit different what kind of things are grown, if it's potatoes or if it's tomatoes and so on. You see here on the bottom right, this is drip irrigation. So the drip irrigation also here, you see the dripper. So if there are algae in, this is really blocking the function. And another thing is, and this is a theme with many people, this is evaporation by having this in the air, but also odor. So a comprehensive water management is usually done in farmland irrigation. And I had in the last couple of years many discussions with experts. And in general, they are quite open for improving the overall scheme of using their water, which is rare naturally. So here, this is just an example. What you see here is one reservoir. It's from screenshot from Google. And the idea of that slide is that there are no other reservoirs, but they could be combined. So farmland irrigation can be improved by pumping water from one side to the other, even when it's well water underneath of all these fields here. So it would bring more flexibility on the fields to use the water where it's mostly needed, and also the reservoirs could pump the water with their own electric power without using the grid. Okay, here again, which kind of water is used? So it can be all sources: rainwater, surface water, tertiary treated water, and well water. So all this mix of water sources need a hydraulic buffer. There's no other way to organize it. And then the hydraulic buffer needs electric power and a pump system, etc. So this can be the function of such a reservoir. I'll show you some slides about installation and logistics. Although this is, there are everywhere are experts to do that, but the floating cover is fixed on a circular rim beam made of concrete, as you see here. So this rim beam is about 20 centimeters in width, 40 centimeters in the soil, and about 20 centimeters or so up on it. And the membrane can be installed while it's filled, but of course it's much easier to empty the reservoir and to install the cover first in the first phase when there is no water in. So it's kind of construction work. So also there some engineering is needed, typical contracting. So this is the empty reservoir. Again, it was 20 years old, so there was some sludge in, and that's a question we are discussing with all clients now. The condition of their reservoir. Sometimes when the reservoirs were built even before 20 years, 30, 40 years, so drawings are not available. So there can be surprises, of course, but on the other hand side, it's not that complicated technique. So all these surprises can be solved now when with the feed-in pipe or whatever. When it's damaged, it can be solved. So the sludge can be removed. That's all rather simple things. There's a liner, by the way, in the reservoir. Usually in all reservoirs, there's a liner. This is a rather simple foil, usually made of high-density polyethylene. So this liner has to be repaired. So in order to carry out a turnkey project, this is what I want to say here, a really good and close cooperation with the owner of a reservoir is necessary. And not all these details can be calculated. That's also important to understand because it's under the water, so it's not visible. So this is when contracting is done, this is also an important part of it. Okay, here's some impressions how we worked. All in all, of course, it takes time. It should not rain, etc. Yeah. Okay. So then the floating cover is supplied. When it's supplied, it's about 8 meters in width. And then a special team, which is able and experienced to install that in short time is needed. And we are working with a very experienced company. This is, of course, not done by ourselves, but they install that reservoir in 2 weeks or so. It was finished. Okay. So here you see again the panel. All right. Now a word about economics, and this is the last part. So as always, we have to look into capital costs. This is engineering, must not be underestimated. The materials itself, the panels and the installation costs. Of course, the panels dominate the overall costing, like always in photovoltaic. Logistic and installation is like everybody who is familiar with EPC contracting knows you need to be well prepared. No surprises. And then the operational costs. The operational costs are very much influenced also by the photovoltaic, even if this is a technology where are naturally not that very high operational costs, but the cover almost cost nothing within these 20 years. That means one of these submersible pumps might be damaged over time or so, but it's not that problematic. Since this innovation is a real niche, or is focusing in a niche, a comprehensive project study has to be done. And that means the reservoir owner, who of course has immediately some questions when you address him, they should be willing to spend money on it. So there needs to be a technical, economical, legal and logistical study. And in my opinion, we speak easily about 50,000 euro per reservoir for such a study. The cost of land is decisive, of course, for the overall costing. Usually the argumentation goes when there's land available, then of course installing a state-of-the-art, rather simple photovoltaic plant costs less than a floating cover. This is in general correct. But of course, like always, project by project has to be compared. Sometimes it's not about costing. Sometimes I learned it's about who is the owner of the land, and not everybody is willing to lease his land or to sell his land. So the basic idea, having the floating cover as a photovoltaic platform, really pays off there. So I mentioned before the hydrobiological study has to be done, depends a bit on the retention time of the water, so how long is water staying in the reservoir. This is quite an influence. And the feed-in tariff scheme, the energy yield simulation, and the typical photovoltaic engineering parts, electrical loading profile. So it can happen. I was discussing many projects now in the meantime, so that a water company doesn't understand immediately what you want from them if you speak about electrical loading profile, because it's not that important for them. They look into their invoices and that's enough for the electric power. Then off-grid PV system and self-sustainable operation I mentioned. So this is also project by project should be examined if you compete against diesel or not, or other methods. So, and then just an advice, if anybody wants to go into such projects, so the study shall be carried out jointly with the buyer and the vendor. So, I mean, usually there's an engineering company in between, and that's the best. Also legally, of course, that's the best, and usually it's a must. But I learned when you do innovation, it's not that easy that there's an engineering company just taking over. So it needs to be, legal conflicts have to be avoided, and now we are in some projects which have delays because of legal questions, because we as a vendor cannot do the study. But on the other hand side, I must say it's extremely time consuming if we are not involved, because we have all this experience now. All right, so this slide shows, this is an example I did for northern Germany, when rainwater is consumed by reservoirs newly built in order to collect or to harvest rainwater. So it shows the benefit of gained water for irrigation, but I don't explain this now in detail. This is similar. Here I can go back. So, here a reservoir with 6,000 square meter will roughly produce in 520,000 kilowatt hour per year. This is quite a number. And also I want to mention here the electric power for irrigation technology is relatively high, because these pumps work with 10 bar, up to 10 bar or even 12 bar. So there's a lot of electric power consumed. And this is one driving force behind all this technology. Now the conclusion, exchange of water in between separated field sections via connected self-sustainable water reservoirs. I don't know from the audience, whoever was in really large countries like Australia, Saudi Arabia, I had their water projects. So for these countries, in my opinion, it can be interesting to examine such a concept. Concentration of field irrigation to local focal point via water exchange. This is a positive effect out of this. Storage of rainwater, surface water, well water, etc. So a hydraulic buffer which mixes all different water sources. Then the reduction of power costs by photovoltaic, self-consumption scheme, etc. Prevention of evaporation. This is quite important, algae growth, pollution, odor, etc. And then finally, the double use of land by attachment photovoltaic on the cover. So this is the conclusion of this niche we are into. We have many inquiries of interest. As we know, the water market is extremely fragmented worldwide. And of course, we would be happy to get more inquiries and to discuss this concept again in detail, project by project. And now, thank you very much. So these are again my contact data. And thanks for your patience and for listening.
Thank you, Tobias. So first of all, thanks for a great presentation. And we have some questions from the audience, and I would like to remind the audience that they can still send in their questions. And we have about 10 minutes to discuss their questions, so we have some time. So the first question that came in, I think we already touched upon that a bit, but maybe good to still do the question. So John asked, how does the cost of floating solar compare to ground mounted? And what install costs are you seeing in the industry, and what do you expect for the future?
Well, there are, first of all, it depends very much about sourcing the panels. And we were relatively long discussing with companies producing flexible CIGS panels. But we see that the expectation, due to the fact that the feed-in tariff schemes are extremely transparent and every expert knows about it, that we have to use glass. But I think that was not the key of the question. The key of the question is more technically about subconstructions. And there, I believe we are equal with land-based, but this depends a bit on the accessibility, on the overall construction management. So let's be a bit careful with what I said. Subconstruction for large-scale photovoltaic became extremely cheap. So let's say we are on large scale, we are a bit more expensive, but I can't say exactly how much. 5%, 10%, probably that's too much. Something between 5 and 10% or so.
Okay, thank you. So, and another question came in from Imco. He asked, how will these panels be cleaned? They are horizontal and probably no or little rain in the areas where you deploy them. So, what's the cleaning method here?
Now, the cleaning practically is done, can be done with a steam cleaner or with a regular cleaning devices for photovoltaic. There's water underneath. This water is no salinated water. It's can go up to, I don't know, 400, 500 ppm salinity or so. So in the worst case, there needs to be a reverse osmosis system to desalinate the water for cleaning. Or water is used from tap, which is nearby. So it's a question of the water quality. The practical part is very easy because the rainwater removal pumps in this trench you have seen will collect the water and the dust or sand and pump it out like the rainwater as well.
All right, thank you. Then I think you already mentioned that you use glass modules, and that was a part of the next question. But is there a limit to the module weight that you can handle with this installation?
No, not at all. Not at all. The module weight, the panel weight, even if it goes up to 25 kilograms, it's no deal.
Okay.
You can send 10,000 people over this foil. The tensile strength is extremely high.
All right. And what will be the influence of flexible installation on cell cracking? Do you have any problems with that?
Yeah, we have not faced that for the time being, but as I said, we've been quite conservative, so we put some, let's say, stable foam underneath of it. The panel we have used, which you saw on the photo, are fiber reinforced plastic encapsulated. So what we say that the panel must not be walked on, but these panels were developed for roofing, and we have not seen any crack yet. I would say this problem is not more, not less than for a roofing application.
All right. And a question coming in from Guillermo. Which environmental and water parameters do you measure to monitor the performance ratio?
Yeah, we have ignored the water temperature yet. As I mentioned before, we have operated for 5 years a test reservoir in Israel, and we installed a lot of measuring devices also for temperature, but at the end of the day we decided just to ignore it, and we designed it like a roofing system. So that means the environmental temperature on the spot, which we took from PV Sol.
Okay, all right. And questioning coming in from Martin, do you have any insights or a view on the market opportunity in megawatt peaks of floating solar in Europe and maybe even worldwide? And then floating covers, so this installation type.
Our innovation suffers a little bit from the high costs of the membrane. So if a reservoir owner has no problem with his water quality, this innovation is simply too expensive, frankly speaking. No need to make a secret out of it. The photovoltaic, as I said, might be equal or a bit more expensive, but the technology of installing this floating cover, doing the engineering, do the pre-welding and all that, needs to pay off in improving the water quality. And if you speak about Central Europe, Germany, Netherlands, Poland also, there's not that water scarcity which justifies it. So this is quite different in other countries, in Greece, in Spain, so in Portugal, I've been in all these countries, discussed it. So there it's quite different, but the water cover has to be paid off by improving the water quality and not by the photovoltaic.
All right, okay. And yeah, as it's specifically then targeting warmer countries, it might not be a super urgent problem, but what about snowfall on the on the modules and the covers. Is that of any issue?
Yeah, probably it is. Well, when it's completely frozen, because the water stays horizontally on all these equipment. So we have not yet considered or planned a plant with a air temperature below 5 degrees. But I can imagine it will be a problem. Yeah. And so we have decided, we have drawn a line and said below 5 degrees we don't go into the project.
All right, okay, that's good to know. Then I want to thank you again for today's webinar, and I think if it's all right with you, if people have any more questions, they can either contact me via the email address on the screen or directly to you. And then for now, I think it's time to round up. I just want to mention our future grid labs in December, the 6th of December, the 12th of December, and the 14th of December. We'll have future grid labs on microgrids, on the economics of energy storage, and on floating solar PV. I want to remind you that tonight is the expiration of Future Grid Week, which can give you a 20% discount on these future grid labs. And I hope to see you all on one of our next webinars or during these future grid labs. And then thank you again, Tobias. And thanks for joining the webinar to the audience. And that's it for today. Thank you.
Yeah, thank you.